talk about routing for a few minutes. The objectives are understand the features and functions of IP routers, such as path selection, routing tables, routing algorithms, and routing metrics. There are a number of ways to set up routes. And the two basic ones are static and dynamic. Static can be used if you're the end unit. And actually you can use a default route static if you're the end unit because everything goes in one direction. If you're not, there are a number of different protocols, and we'll look at them briefly as we go through this one. And it says the functions of and distinctions between routing protocols RIP, EIGRP, OSPF, IS, and BGP. And we're going to have internal routing protocols and external routing protocols when we do this. And the only external routing protocol is BGP, which is Border Gateway Protocol. And it's the thing that the internet runs on. Understand highly available fault-tolerant routing design. We have multiple routers. This gives us the fault tolerance for that. Install and configure and troubleshoot basic routers using command line tools. You can use a Windows machine as a router. Years ago, I used a Windows NT4 machine, so you know how long ago that was as a router, because I had a spare laying around and I had a license available for it. And it worked okay. Routers themselves, the devices routers, are optimized for packet forwarding, and that's what we're doing with these things. The routing basics here, when a machine computer tries to send traffic from someplace, the first thing it's got to determine is if it's a local or remote host for the destination. If it's on the local network, after it does the ANDing and determines that the network address is the same for it and where it's going, then it simply ARPs for the MAC address of that device. If it's not, it ARPs for the MAC address of the router, and then the router goes on down the line until it gets to the location where that network is located. I'm going to bring up a couple of packet tracers, one EIGRP, and we'll get to the protocols. One's EIGRP protocol, the other one is a RIP protocol, so you see a little bit of the differences in them. Routers are what's called intermediate systems, and the end hosts are the non-routing hosts, end hosts, our computers here, my computer, servers, things like that. Anything that's not routing is an end system host. And the host got to use a router to get to remote networks, which means that we also have to have the default gateway configured correctly, because the default gateway in the IP address is the address of the router that's on our network. Routers are IP hosts configured with multiple interfaces. You need 2 interfaces in order to make this thing work, because it's going to go from one side to the other. Could be a server or workstation, kind of a workstation. You can use a Windows workstation to share the internet. You can do routing with a Linux workstation, but actual routing, I think, with the routing and remote access, which I believe they're going to have you configure, is only available in a Windows machine. In most instances, what we're going to want is a dedicated router appliance. Use the same sort of process to forward packets to the destination via a complex internetwork. Paths are recorded in the route table, and what's in the route table, and I copied this from one of the routers that I have. The gateway of last resort is not set. The gateway of last resort is going to be what's called the default route. The default route is the one, if it can't find anything else, that's where it goes. And typically, if you're going to an ISP from a location, that's the only route you need out. But you'd have to have other routes internally. And this one is actually an EIGRP. What each of these things means, try a different thing here, try the spotlight here. C is connected. And this says it's directly connected, and this is the port, the fast Ethernet 00. The D here is an EIGRP, and it has the metric. So the destination network address, along with the subnet mask, the gateway or the next hop address, and this one via 192.168.4.1, that would be the next hop. That'd be the next router down the line. And then the interface that is going to go out of. This one here is a last update time on these things. So we have the ability to do these things, to see these things. And the metric, this is the metric here. EIGRP metric is pretty complex. We'll just say that that is the metric. We have a metric, and then the interface that goes out. You can actually either usually give the next, this gives both the serial interface, the interface that's going out, as well as the next hop address. Routing tables and end systems. This one kind of shows what they're doing is showing what they want to. Let me start up one of my packet tracers here and see what it looks like in those. Let's look at a RIP when we go in these things. I've got so many things going here that my packet tracer's not starting very quickly. Okay. If we go over here and then we'll go into the greens say that it's all running, and notice that we have spanning trees still starting up over here on both of those switches. So those are there. We have our end systems and our intermediate systems. So if I go into this, figure out where it went on me. It's changed the state, so it's up and running, the system's up and running. We can show the IP route. This is RIP, and R means RIP, and we have the destination network address. The administrative distance or the metric that it's going to use, and via, this would be the next hop, and then the interface is going to go out. So those are all going to remain the same, and these things do actually work, end system to end system. What this kind of, and I'll probably make a mess out of it, but we can actually put these little packets here and watch them go. And let's see if it actually works. It goes on to switch. Shouldn't be any difference there. We're going to go to the default gateway, which is the router that's on the next hop router, and this one's going back because the next hop set wrong on it. This is one that obviously didn't work back and forth. So what we've really done here is set up a routing loop because of a misconfiguration in these things. This is one I had found that a student had done. This was, well, now we're going, send it back, and now we're going to go hopefully all the way through. When it has issues, I always thought that watching the little packets go back and forth were neat. But anyhow, end-to-end. RIP is what's called a link state protocol. But we have the destination, the gateway, the interface. The gateway, and the gateway is going to be the default gateway on our computer here, which should be this address of the first router, and then it's going the router, and they've got other things here. Destination is 0.0.0/0 with a subnet mask of 0.0.0 is what's called the default route. And the default route, if we don't have a specific route, like one of these down here, if we don't have a specific route, it will send it to the default route. It is the gateway of last resort. So we have our destination, the gateway, how we're going to get there, and what interface it's going out. And typically the interface is going to be the interface name, not the interface address. The next hop is the address of the next router, not where it's going to go. So the next hop address from here is going to be in this location. And the default route says that everything's going to go there. If you're an end unit, an end system, and we're going to the internet, there's no other places for this to go. We can use a default route. It makes it a lot simpler rather than trying to write routes to go to the address up here. And we're certainly not going to write routes to go to all of the machines on the internet. That's what BGP is for. So the packet delivery, we have directly connected routes versus the next hop router and the default route we talked about. The TTL, time to live, how long it's going to live on the network. And the TTL is going to be different. If you look at a TTL on a Linux machine and a TTL on a Windows machine, they are different. But it's how long the packet is going to survive on the internet. When a router starts up, the only thing it knows about is its directly connected interfaces, those networks that are directly connected to it. What the dynamic routing protocols do is advertise to other routers the fact that that's where that particular network resides. The efficiency that happens with is what the routing protocols are all about. Dynamic, so I need to get rid of my marks there. Dynamic static routes are manually configured in route tables, and when you manually configure them in route tables, by the way, they're the most trusted routes. Hierarchical, as we organize routers in domains, backbone, border routers, or flat, all routers are peers to one another. And then we have the hierarchical with a backbone is going to be something that the protocol called OSPF, and OSPF stands for Open Shortest Path First, is going to use. It uses a backbone. And the internal routers can communicate within the domain or out of the domain via the backbone router. So what happens is when we configure these things, they are able to talk within their own specific area, their own specific assignment, but if you go outside, you have a router appointed to communicate outside of that area. And that's going to eliminate a lot of the traffic on router updates if you get them from a single source. Flat, all routers are peers of one another, and I think RIP's going to kind of be in that instance. And each network ID requires a separate routing entry table. That's going to become kind of complex as we go down the line, because we really don't want to have to put all those routes into the router. Once you get them in, you don't change them all that often, but dynamic routing makes it a little easier on us. If you have something simple like a default route, you're the end unit and you can only go out one way, then default routes work pretty well. You can create some really cool routing loops by doing that, though, by having default routes. The distance vector propagate the entire routing table, and distance vector is slower convergence. Convergence is when all the routers have the same information. But distance vector is going to be RIP. RIP's a very old routing protocol. It uses RIP version 1, still uses classful addresses. You cannot put an IP or a subnet mask on one of those. A linked state routing protocol, OSPF, is one that only propagates the updates. Once the routing hierarchy, the routing topology is known to all of the routers, then you, instead of sending the entire route table every time. You only send the changes to the route table. It makes it a lot more efficient to do it that way. And again, convergence is when they all have the same information. And that may change at some point. These are the metrics that are available to them the devices. The first one is path length, the distance or the hop count. And hop count becomes important in RIP because that's what it bases its routing on, is hop count. And you can only go 15 hops. If you have 16 hops, it becomes infinity for RIP. Reliability, how reliable is the path that we're going to use. Latency, the delay, what is the delay? It takes time for the packets to traverse the delay, and when I look at the labs that you guys are doing, it actually measures the latency. Mostly they are pretty good, but occasionally we get into good. Most of them have been excellent so far. The bandwidth, based on the bandwidth, look at the maximum achievable bandwidth on a link and don't consider the available bandwidth. Less efficient metric than the delay-based metrics. Delay is probably, or latency is probably one of the better ways to try to determine what the best path is. Load, the link utilization, based routing decisions on how busy a particular route is. And some of these routing protocols will, as they get to the destination, will tell that router that they've experienced delay or heavy load on the path to get there. MTU, maximum transmission unit, how large a packet can be sent. And this is one that we don't really want to get into a situation to where we have to fragment these things, because fragments can be expensive, and price and cost, those can be assigned by the administrators so that you can force it. If you have multiple paths or more than one option, you can force it to one or the other paths as the predominant one. The routing protocols that are available are RIP, which is a distant vector, and then we have interior gateway protocols and exterior gateway protocols. The interior protocols are within our system typically, and they call them autonomous systems, and not real sure that was a good way to describe them in the book, because when we go to get to EIGRP and BGP, they actually define autonomous systems. So RIP can talk to any router that's running RIP. It doesn't really care. It uses UDP, port 520 and 521. Interior Gateway Protocol under the management of a single administrator is a better way, or within a single network perhaps, or internetwork, or campus when we go through those things. Enhanced Interior Gateway Routing Protocol, EIGRP, is an advance from IGRP, interior, which was the start of things. It's generally called, it's a distance vector. It's a little bit of both. It takes the best of both worlds from distance vector and link state. So it is frequently called a hybrid protocol. It's another interior gateway protocol, and it has its own transport layer. It doesn't use TCP or UDP, and it's protocol number 88. OSPF, Open Shortest Path First, is a link state protocol, which means it only sends updates. It's an IGP interior, and it also has its own protocol, and it's protocol 89. One of the differences between EIGRP and OSPF is they both determine the entire topology. when that happens, EIGRP selects it and doesn't save all the alternatives. OSPF keeps all the alternatives. And the way I like to think of this is if you look at Google Maps from an overhead, you get the topology of where you are and where you're going. If the traffic gets too heavy, you're going to look for an alternate route. OSPF would have that stored. EIGRP would have to go out and rediscover everything.
Larry,
Say?
So routing protocols are basically how packets get around through routers and servers?
No, they're how routers share information about what's attached to them, basically, because the only thing they know when they start with is the networks that are attached to them.
So these are protocols on how to link routers?
How to share route information, exactly.
Okay.
That's all they are. And RIP does send the entire routing protocol. It's sometimes called routing by rumor because it shares everything and it sends it to the next router. The router adds a 1 to the hop count and then sends that information on down the line. One of the problems that can happen with these things is if part of a route goes down and the other end has information that says, oh, I know how to get to there, and it sends it back. So these things, and it comes out later in troubleshooting, the routers have something called a split horizon, which says that you can't accept routing information on the interface that you sent it out. So that if you tell the next door router how to get where a route is, where a network is, and it goes down on where it came into you, it can't tell you back that that network is there. IS to IS is a link state protocols, IGP, Interior Gateway Protocol, and it's a native data link at layer 2. BGP is a distance vector which goes back up here, and it is a very slow to converge protocol. The reason is it's the protocol that the internet runs on. And it has to be slow to converge because routers go down and come up on a kind of a regular basis. And if it did that, it would be trying to update these enormous route tables every time a router went down. So it is a distance vector. It does send everything. It is the protocol that the internet runs on, and it has autonomous systems. The two that have autonomous systems here. I messed that up, didn't I? And then EIGRP defines autonomous systems. In EIGRP, what the autonomous system means is that only routers within the same autonomous system are going to update each other. Then you have routers that communicate between the autonomous systems. Autonomous systems, also BGP, which assists it in making the route tables more efficient. Routing information, RIP. This is my slide. It's a distance vector protocol. There are two versions, V1 and V2. V1 is does not use subnet masks. It only uses class full IP addresses. Version 2 you can use a subnet mask. It can be classless. It's an interior gateway protocol. It also, it says on network, it should be used on small networks because its hop count limit is 15. Once you get to 16's infinity, and that route is not available at all. It also requires a lot of communication because when it updates the entire route table. It's a simple protocol. It is very easy to set up. You just go into the router, type router RIP, and then whatever networks you want to advertise. And what these protocols do are advertise the networks that are attached to the router. RIP v2 supports classless. RIP only uses hop count to determine the path. The issue here is if we had two T1 lines, and we'll pick T1s because I picked them up. That's the one that came to mind. Two T1s that go to routers that are connected by T1s that go to a destination, and you have a 56K single connection, it's going to pick the 56K, so it's not a very smart protocol. RIP NG, RIP next generation supports IPv6, but not a whole lot changed, and it UDP ports 520 and 521. 521 for IPv6 and 520 for IPv4. EIGRP is an interior gateway protocol. Advanced distance vector, sometimes called a hybrid. It has more metrics than RIP. It uses reliability, bandwidth, delay, and load, and it is a complex metric to calculate if you ever have to do that. Supports classless routing and has versions for both IP4 and 6. Runs over IP directly. It has its own protocol and does not use TCP or UDP. This is the autonomous systems that I was talking about with EIGRP. In it, only these routers are going to talk to each other in this system, and these routers are going to talk to each other in this autonomous system, and you have autonomous system numbers, autonomous system 200 and autonomous system 100. This router here is called redistribution. It shares these routes with this system, and the same thing happens to the other end. So you have to set a router up so that it can send them from one autonomous system to the other. Open shortest path first, OSPF, is an interior gateway protocol. It's suitable for complex networks. It is the most sophisticated of all of them because it keeps the entire topology. This is one that they talked about the backbone, and it does have a backbone, and the backbone it's defined as areas. The backbone is going to be area 0, and all of the other areas have to touch area 0. So these things and the border routers, here, the area border routers, share the information from one area to the other. Each of them has a different area number. And the autonomous system here would be these routers would be an autonomous system for BGP. And the autonomous system border router is the one that's going to go out here to the internet. It is, again, it is the most sophisticated, keeps the whole topology as well as alternates, so that if something happens and you have to go to an alternative, it can get there much quicker.
So in OSPF, what happens if your backbone router fails?
Well, then you've got a problem. Anytime a router, just like if what happens if your gateway router to the internet here fails?
The backbone router would take down the entire network though, correct?
Yeah, well this does too, effectively, because everybody's worried. I know there are other things on the network, but the first thing you're ever going to hear is the internet's down.
That's why you set up redundancies for your major routers.
And you have, and that's the next thing it's going to be is we set up redundancies and a different protocol for that, HSRP and VRRP, so that we would have multiple routers on the same path. It takes a lot of resources. It depends on how important that resource is, how much money you're going to spend on it. But you're absolutely right. There are a lot of single point of failures in a network, although we try to avoid them, you just can't. IS to IS is a linked state interior, similar to OSPF. It doesn't have the backbone. It has different areas, so the back to the, you won't have the failures. It has a little bit more flexibility. But of all the Cisco classes I've taken, the only protocols that they really talk about are RIP, EIGRP, and OSPF, and they don't recommend that you use RIP typically unless it's a pretty small network. IS-to-IS is there, it's supported, but in all of the certifications, the CCNA and the CCNP, they've never really said a whole lot about IS-IS. Border gateway, it says distance vector mostly, usually deployed as an exterior. It can be deployed as an interior gateway protocol, but it's typically going to be an exterior. And it replaced a protocol called BGP, Border Gateway Protocol. It supports routing on the internet, and it uses the autonomous systems, and it uses that to hide the network complexity. This is where route aggregation becomes really important, because there are lots of routes within the whole world, and that's where ISPs get. ISPs are typically where the autonomous systems are going to be in here, so that BGP sends the traffic for the entire Cox cable or whoever to them, and then they distribute it on their own network. They use autonomous system numbers, exchange autonomous system. But yeah, this is a lot of autonomous systems here. Between autonomous systems, they exchange information. Supports classless routing and runs over, this one runs over TCP port 179. The metrics, administrative distance here, are the things that are going to determine how trusted the route is. So when we're looking at these things, the local interface directly connected, and the lower the number, the better, has a 0 administrative distance. It's absolutely the most trusted. The static route is a 1. It is trusted more than the dynamic routing protocols. BGP 20, EIGRP 90, OSPF, IS-to-IS, and RIP. RIP is the least trusted of all the routes. And this is if you have multiple routing protocols on a single router, and you can have more than one protocol running on a router. And whichever protocol has the lowest administrative distance will be the route that will be used on that system. IPv4 sitter introduced in the 90s. That's the /8 sitter blocks are allocated at the regional internet registries after they're allocated from IANA, and IANA is the organization that controls the numbers. They're the numbers people. The regional allocate blocks to the ISPs, and then the ISPs divide their allocations up. So what they try to do is get the IP addresses grouped or aggregated so that you don't have to have as many routing entries in the systems. IPv6 is designed as a hierarchy. The global unicast address space at least is, and have top level allocations. The customers get allocations from the 48 from the /48 for the big organization to the 40 to the /64 for the home user. When we get into IPv6, you're going to get a lot more addresses, and I think that's one of the things that the ISPs haven't figured out how to do yet. But you'll get more addresses, and you'll be able to do your own subnetting, and they will be public addresses. Back to the question that you asked earlier, what happens if that single router goes down? Yes, we have a problem, and that's what the high availability, the hot standby router protocol and the virtual router redundancy protocol are for, VRRP and HSRP. HSRP is a Cisco proprietary protocol. VRRP is not proprietary, so it's an open standard. One of the things that Cisco at least likes to do is go in and give you something that's not a Cisco to connect to, and you have to figure out the correct protocol to use. In this case, if it's open standard protocol, VRRP, if it's all Cisco network, you can use HSRP. But this was what you would do, and what these things essentially do is provide a virtual MAC address and a virtual IP address, and the management software within the routers, and they all connect to a single switch, and then the one that does the descent, one of the routers will be configured as the management router, will determine which physical interface to send the packets to. That way we don't have an issue with everybody else trying to find the correct default gateway, because both of them get traffic to that particular IP address and that particular MAC address, virtual ones. And then if one of them goes down, the other one can take the entire load. But that's one of the ways to overcome the single point of failure. And that would be in a high value unit, because when we start doing these things, when we start doing things like high availability and all the things that would make our network much better, much safer, you start getting into some pretty significant costs. The router appliance, and this is an HP router. This is what this is what it's going to look like on the business end, which is usually the back side of it. We have some Ethernet ports here. A console port. A console port is an RS-232 port. Probably one, you can't see it, but I would expect that there at least one of these RJ45 connections here is going to be a console port. Otherwise, you're going to have a 20 or a serial connector to go to that, and you'll have to go from a serial to an RJ45 to get to your computer. When you make a serial cable, for Cisco anyway, you need to do a rollover cable, 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1. The software, the network operating system, a router is a multi-home server. A router is the router software operating system is optimized for packet forwarding, for managing the packets. So it's a computer, it's a specialized computer. It doesn't have a keyboard, it doesn't have a monitor, so we have to connect to it with something else in order to make it, in order to do the configurations on it. Once you get it configured, you can telnet or SSH to it. Telnet is a not secure protocol. It is not encrypted at all. SSH is secure shell. It does create a secure link when you're managing the computer. Router placement becomes an issue. Where are we going to put them? How are we going to manage these things? This one shows everything in these VLANs going up here to the router, and this will be a layer 3 router, and it can then route. It can have virtual interfaces, and it can route between the virtual interfaces and come back. So traffic would actually go from this VLAN up here to the router, get routed from virtual interface to virtual interface, and come back and go there. If you don't have a layer 3 router, you just have a router, or excuse me, a layer 3 switch, you have a layer 3 router. Then for VLANs, you can do what's called a router on a stick, where you configure the interface as a trunk port, and then you have the virtual interfaces that get routed inside it once they get there. Configuration, SSH or Telnet, or the console port. Console port, you connect directly to the router from the serial port on the computer. Network interface and the loopback interface, those are all available. Loopback interfaces are virtual interfaces on a router. configuration tools. Let's see, the route. You can see the route on your machine by using the route print command. You can also see it on a Linux machine, but this one shows the default route 0.0.0.0 with a mask of 0.0.0.0, which is the default route. Goes to the gateway, which is 192.168.1.1 is the gateway. 192, oops, I didn't mean to do that. 192.168.1.3 is the interface on the computer itself. The loopback just goes to its own self. To go to its own network, the gateway is going to be its own NICS address, and you can look at the rest of those. But if you want to look at the route table on your Windows computer, it's route space print in order to get to those things. These are troubleshooting systems. And with path ping is kind of Microsoft's attempt to do more than traceroute. Traceroute has always done enough for me. The Looking Glass site is something that reveals the configuration. MTR. What I wanted to show you, we talked about routing loops, and I found one today. I think they probably fixed it by now. If I ping ranger.ecpi.net, we get a TTL expired in transit. That typically is going to be the time to live expired in transit. We didn't get any answer from it. If we do a trace route, and if we do a -D, it doesn't do the DNS resolutions, which makes it much faster. Okay, now we're out on the internet with all those good routable addresses. This one slows down. It will get past this. Okay, now we go. Now it's starting to go back and forth, and this is probably due to, it'll quit here in a second, or I'll make it quit. Due to static, or due to default route. So it's going to 15.1 address, and the 15.1 address is not finding a way to get to it. So it's sending it back to the 15. The 2's first. The 2 sends it to the 1, sends it back. So it just goes back and forth because it doesn't have a route. It's an improperly configured route to get there. And that'll go on until the TTL has expired, and it'll drop it. Packet circles the network until the TTL is exhausted, which is what we just did, usually caused by misconfiguration, and we use traceroute to diagnose it. When you use traceroute, where it fails, that router is where the problem is. With that, features of IP routing. Actually, what we need to do is the questions, don't we? No. What is a directly connected? I'm sorry. Somebody a question?
Oh, you said, I guess we need to do the questions. I said, nope. I was just kidding.
Oh, well, I've been looking at the test banks for the questions on these things. The IPv6, the only question I can see is what does the loopback address look like? The only questions that I've had on these tests, including Cisco, are is this a valid address, and what is the basic ones that we talked about earlier, the local link and the global and those things with the prefixes. So you're not going to have to go. You may have to figure out subnets on an IPv4, not actually do true subnetting, but figure out how many hosts you need. But I don't think you're going to get any very in-depth IPv6. Routing, I don't know. I've got to do a little more looking on it to see what kind of questions that they ask on it. But it would probably be things like the basic basic, what are the basic protocols? What's a link state? What's a distance vector? Those kinds of things. What is a directly connected route?
Static.
That was directly connected to the router. When we, and I should have left that one up. When we have these things, I'm gonna put a different router up. When you look in the route table, it'll tell you which protocol it got that route from. If it has a C beside it, it means it's a directly connected route. On this one, each of these, and there's not a whole lot on it, but each of these would have the ability, well, it would too because they have IP addresses, to have a directly connected network. So this one, whatever it is, and we can go into it and look at that stuff. So it is gotten its stuff. So we have directly connected 192.168.2.0, and we have 192.168.5.0. When we configure the protocol, we tell the protocol which of these networks we want the world to know that are connected to us. If you have networks that you don't want to show, then don't advertise them. And it then, using whatever protocol we've selected, tells the world, and typically it's going to communicate with the next router here. So we'll go down here and it will then tell it the next routers, what networks are directly connected to it, and these will do the same thing, so that eventually it builds the routing table so it has the topology of the entire network that it's a member of. Again, depending on whether it is EIGRP, which uses autonomous systems, or OSPF. But all of the autonomous systems or areas will communicate only with the routers that are assigned to that autonomous system or to that area. But all the directly attached networks are the ones that are advertised. You can't see them there. I thought you could. An entry in a routing table was used to table will list the destination network address and net mask plus a gateway and metrics. What other piece of information is required? What do you think? What other information? We have the destination network, the subnet mask, the next hop. Was that there? Destination network mask, and metrics. So what do we have to know before we can get somewhere?
Protocol.
The next hop. Where's it going to go to next? Routers are kind of like your GPS. GPS has a lot of information, but what does it tell you? Where your next turn is? A router tells a packet where its next router is. It doesn't give the packet the whole topology. It just says go to the next router, and the next router looks at its header information, and then tells it where to go to the next router, and it does that one at a time to get across the internet. With all that going on, isn't it amazing how quick things happen?
Faster than my brain.
Faster than my brain. Everything's faster in my brain. If a routing protocol carries a subnet mask field for route updates, what feature of IP routing does the routing protocol support? If it takes a subnet mask with it, what does that mean? Is it a classful or a classless?
Classless.
Classless. So you can do subnetting and supernetting with it. And the only one that is class full is going to be RIP v1. The rest of them are classless, or they take the subnet mask with it. Carries the subnet mask field for the route updates. If it doesn't, then it's going to be a class full. True or false? A router would normally have more than one network interface. I'm sorry?
That's all but RIP then?
Yeah, RIP's the only one that's class full. And RIP v1 is a very, very old protocol. It's a very simple protocol. It's a piece of cake to configure, but it's also not very flexible. Which means that if you've tried to subnet within your network, it's going to pick up the class full address. There are ways to trick it into working for you if you had a network subnetted on a router. If all of the subnets were on that router, once it RIP sent the packet there, then the router could then send it to the correct location. If that made any sense at all. A router would normally have more than one interface. True or false?
False.
A router would normally have more than one interface.
False.
Well, we repeated the question after we said false, so I guess it's true.
Yeah.
The external and internal connections.
Here we go. A router has, I mean, if it only had one interface, how far could it go? How far could it route?
Nowhere.
That's true.
They normally have at least two, and sometimes they have many more than that. On a layer 3 switch, which is a router in hardware, probably going to have like 24 ports on this, something like that.
Sorry, it was 50-50 and I went for it, guys.
It's a 50-50-90. Let's see. What does it mean if a routing protocol converges in a steady state quickly?
Say again?
What does it mean if a routing protocol converges to a steady state quickly? It means that we have quick updates and it's a stable network.
That's a trick, kind of a trick question.
I know.
That's a
Right.
conversion.
That's what I was thinking.
You want a converged network, but it did it quickly.
Yeah. It's one of those, huh? Which general class of routing protocol provides the best convergence performance? And the two are link state and distance vector. So which do you think? Which would be quicker? Well, if we say link state only sends the updates and distance vector sends the entire route table. Which do you think is quicker now?
Link state sends what?
Only sends the changes.
Well, that would be quicker.
Yeah,
Yeah, that'd be quicker.
Yep. What routing metric might you prioritize for a VoIP application? The answer to this one, and it's a big deal with IP phones, is latency delay, because they start breaking, the conversations start breaking up. It needs to be, delay needs to be consistent. And VoIP is becoming a bigger and bigger and bigger deal. What is the shortest path bridging? The slide was there, but I don't think I talked about it. It's a means of IS to IS routing matrix to establish layer 2 switching paths as an alternative to using spanning tree.
OSPF? What is shortest path?
IS to IS.
Oh, IS.
What is an autonomous system number and how does it assist route aggregation?
I just saw that.
It just takes groups.
Yep.
Groups.
Groups them based on
The local network.
Yep.
Or large network. Whatever.
when might an administrative distance metric be factored into routing decisions?
Say it again.
When would a administrative distance become used? When would the router use the administrative distance?
Something have to do with cost.
About if we have more than one routing protocol. Which one are you going to use? What is the purpose of HSRP and VRRP?
Reliability.
Reliability, redundancy. How would you view the routing table on a Linux PC? I didn't give you the command. I kind of did. Windows is route print and Linux is just route. And on Cisco, show IP route. If you received a request timed out error message when using ping, what tool could you use next?
Trace route.
Trace route.
What is a looking glass site? And
Did we talk about that?
And I didn't do that very well at all. I kind of said, yeah.
The last thing.
It's a service that allows third parties to inspect the routing infrastructure of an autonomous system to assist in troubleshooting.
You say that again?
A server allowing third parties to inspect the routing infrastructure of an autonomous system.
What was it called?
A looking glass site. What this would do is allow the third party, a trusted third party, to look at the infrastructure to see if they can figure out what's going on with the when you have a problem.
Could you go back to 10?
10. When would an administrative distance be factored into a routing decision? If you have more than one routing protocol on the router, because you can only have one route and one protocol. If you have multiple protocols, you're going to take the one from the most trusted one, and the most trusted is going to be the one with the lowest administrative distance.
So that's having multiple routing protocols.
Multiple routing protocols, yeah. If you have like RIP and EIGRP, you're going to trust EIGRP, and you're going to trust everything over RIP. If you had a static route in any of the dynamic routes, the static route is going to be trusted. It's going to have the lower administrative distance.
And the system would just automatically pick the most trusted route.
Say that again. The administrative distance is automatically picked up based on whatever the routing protocol is. That's something that's programmed into the system based on the routing protocols.
So is that another item used in redundancy? Is by making multiple protocols?
Kind of. What it usually winds up being is, I was going back to the table if I can find it. Here's the table. What it usually winds up being is that you have OSPF running one place and EIGRP running another place. And
You get
when you combine them on the single router, which route is that router going to use? Because it's going to redistribute the EIGRP into OSPF and the other way around.
So like when you have a backbone router on the
Mm-hmm.
SBDF or whatever.
OSPF, yeah.
OSPF. If it's also connected to an ISIS, you would just stick with OSPF because it's more trusted?
Yes.
Okay.
The ISIS route would still be there, it just wouldn't be used.
Okay.
So we got a few minutes to do some more lab work.
Finish 8.
And you can finish 8 and work on, I guess, 9 if you get there.
Yeah.
I didn't want to go that far, did I? There it is.